Welcome to The Explainer. Today, we're diving into a really powerful statistical tool, one that helps us make sense of a world that's constantly in motion. We're talking about data that curves and dips and changes, data that doesn't just sit still.
All right, let's jump right in with a simple question about something we all do constantly. Talk. Imagine you're trying to describe the sound of a vowel. It's not just one thing, is it? It actually changes from the very second it starts to the moment it ends. I mean, sure, you could just take a single measurement, a snapshot in time, but that's kind of like trying to describe a whole movie by showing just one single frame. A sound isn't some static point, it's a dynamic journey.
And that journey, it creates a shape. As the frequency of a sound changes over milliseconds, it literally traces a path, a curve. And this wiggly data, as statisticians sometimes call it, is a real challenge to model properly. So when you're faced with this wiggly line, what's the first thing you do? Well, the most common first step in statistics, the thing we all learn, is to try and fit a straight line through it, using a method called linear regression. But, well, you can see for yourself. A straight line is a terrible fit here. It completely misses the rise and fall of the data. As the source material puts it, it's just completely unable to capture the reality of the curve. But here's where it gets interesting. The failure of our model actually gives us a really powerful clue. See those distances between our straight line and the actual data points? Those are called residuals, or errors, and when we look closely at them, a pattern starts to emerge. You see, if our model was a good fit, its mistakes would be totally random. Some high, some low, no rhyme or reason at all. But here, the errors themselves form a curve. A clear pattern in your errors is a massive red flag. It's basically the data screaming at you that your model's fundamental idea, in this case, that the relationship is a straight line, is just wrong.
So if a rigid, straight line doesn't work, what do? Well, we need a tool that's way more flexible, something that can actually bend and adapt to the data's true shape.
And this is where we see this major shift in thinking. We're moving away from a linear model, which is like trying to measure a curve with a rigid ruler, and we're moving towards an additive model, which is much more like using a flexible wire that you can bend to trace the curve perfectly. In statistics, these flexible wires are called smooths, and they're these incredibly clever functions that can automatically adjust their own wiggliness to find the best possible fit for the data. These smooths are the additive part, the A, in a model called a GAMM. And wow, what a difference it makes. Just look at that. The additive model, using that flexible, smooth, just elegantly follows every single nuance of the data. It succeeds where that straight line completely failed. So, problem solved, right? We've figured out wiggly data. Or have we? The thing is, the real world is rarely that simple. We almost never have just one clean, perfect curve to look at. Instead, we have groups of data. For example, what happens if we record that same sound, but from 10 different speakers? Each person is going to have their own unique vocal qualities, their own distinct curve. And this is key. We can't just average all those unique curves together. If we did that, we'd lose all that rich individual information. What we need is a model that's smart enough to see both the overall pattern, the forest, and the unique shape of each individual trajectory, the trees. So this brings us to the second half of our solution. This is where the M for mixed model comes in, creating what we call a Generalized Additive Mixed Model, or GAMM for short. A GAMM is just brilliant because it models the group and the individuals at the exact same time, building up the complexity. It starts with something called random intercepts, which takes the average curve and just shifts it up or down for each person. Then it can add random slopes, which can also tilt or stretch that curve for each individual. But the real magic, the breakthrough, is in the final step, random smooths. Here, the model gives each and every person their own unique flexible wire, capturing every subtle difference in their trajectory. And that, right there, is the full power of a GAMM. It learns the shared underlying pattern that's common to everyone, while at the same time modeling all the unique variations that make each individual different. Now, you might be sitting there thinking, okay, this is all just a very technical, statistical detail, but getting this wrong, ignoring those individual differences, has massive real-world consequences for your research. Get this. According to the research this explainer is based on, if you analyze data from different groups, but you fail to account for the unique shape of each individual's data, your false positive rate can skyrocket as high as 60%. Let me put that another way.
you would have a 60% chance of thinking you've found a meaningful, significant result, when in reality, you've found absolutely nothing. You'd be fooling yourself with statistical overconfidence, all because your model wasn't smart enough for the data.
This slide shows us exactly why that happens. Look at the gray area. That's the model's uncertainty. The simple model is super confident with that very narrow band, but it's a false confidence. As we add the right layers, the uncertainty band for the full GAMM gets wider. The model is less certain, yes, but it's also more honest. It's accurately reflecting the real complexity in the data, which protects us from making these false discoveries.
So let's just quickly recap the main takeaways here. The world is wiggly and it's full of individual variation. Simple models just fail by oversimplifying everything. GAMs give us a powerful solution. They use those flexible smooths to capture complex shapes and a mixed structure to respect individual patterns. And what that does is give us a much more honest and accurate picture of our data. And that leaves us with one last thought. From tracking economic forecasts or disease outbreaks to analyzing climate data, our world is just filled with these complex, wiggly patterns. It really makes you wonder, doesn't it? How many of our big conclusions about the world are based on trying to understand a beautiful, complex curve with nothing more than a simple, straight ruler?